Hi engineering students. This is the second video for week 4 and I want to start by seeing if anybody has had any more thoughts about the mechanical or electrical furniture that I mentioned to you already. So this is going to be our first major project, and we are going to get to work in a serious way in just a few more weeks. So I want this to be kind of like a background process for you. You might see things in magazines, online, you might see something in someone's house, in your own house, and I want all those ideas just beginning to accumulate. So I'm going to show you some ideas of the kinds of things I'm talking about, but before I do that, let me say that I'd like you to use your discussion board question for this second half of the week. I want you to make that a suggestion for what you think would be a good solution along these lines that we're describing. Now, we probably are going to get, I think I can get it together, I think it's happening, actual suggestions from our friends at PathPoint and maybe some teachers at school here as well. So we might have to bend it along the lines they're asking for, but in the meantime, I want you to suggest a type of, electrified or like mechanical, like some kind of electrical mechanical furniture that you think would work really well. So here are a few things on the screen right now, just as I was looking around. Firstly, I think plywood, nope, I don't want that, go away. Okay, there we go. Plywood is going to be a really good option for us. It's relatively inexpensive, it's easy to cut and manufacture and put together, and if you do it right, it can look kind of stylish as well, kind of like modern style. So here's an example of a DIY chair, which would be very strong. They've supplemented it with some leather. This doesn't have any electrical or mechanical component, but just trying to get you thinking about what do-it-yourself wooden furniture tends to look like. Here's just a very, very simple desk, which would not be hard to do. And I think this one, it's not like electrified, but it has adjustable legs. It could be raised or lowered. So imagine having this, but with some actual electrical actuators, or maybe like a little winch or something that goes up and down, and that raises or lowers the height. That'd be really cool for, doing hands-on projects where you want to either be standing at a desk and then you want to adjust it and be sitting down, things like that. Here's another example of simple plywood furniture. When you're thinking of plywood furniture specifically, as opposed to other types of wood, I find it helpful to think of like paper or cardboard. For those older students who worked on Mr. Mitchell's plywood boxes and things. Actually, I don't know if any of you guys did that. That was the other group, but you've seen those ones that he uses. We started that project by folding together sheets of paper and card to make little mini quick scale models, and that was really, really useful. So imagine like cutting out bits of card, and I will have you do this, of course I will. And what kinds of rigid structures that are still strong and elegant and efficient could you make? Here's an example of something which is electrified in the sense of lighting. Okay, you could easily have a desk for someone that had like a little rim around it or a shelf or something, and hidden under that shelf is some simple, inexpensive LED lighting which plugs into mains power or even is battery powered. That's definitely an option. And it would look something like this. Not as big and complex as this, although I should say I'm just interested in the lighting for this picture. Here's another lighting idea. This is more like specific art equipment where you build a light box. You've got lights underneath a translucent sheet of acrylic or glass or something, and it actually shines through so you can do tracing really easily. I think that would be a cool idea at some point. The PathPoint people love to do art therapy with their residents, so yeah. Alright, so I hope that's got some good ideas for you. I didn't find it easy to look and find things, honestly. When I started typing in keywords on the internet, like, mechanical furniture or electrified furniture, I got some electrical chairs come up when I typed electrical furniture, which is not what we're doing. So it takes a little bit of searching, and I think, honestly, just a little bit of your creativity. So I put that in your hands. Again, please use your discussion board comments this week to suggest electrical and mechanical furniture that you think would work really well. And then if you want to add beyond that any questions about the math and physics content, of course you can do that, but I do want your primary comment to be about that. All right, well, let's get into the math lesson proper. Okay, so last time we combined our vectors. We were only using graphical techniques. Okay, this was just a couple of days ago. We said this works really well if you have a few things in hand. We said it works great if you have graph paper. Okay, could be one option. Things like rulers, a steady hand, a good eye, or computer programs are a really good way to do this one. So obviously right now I'm using a computer program to do this, but I could be doing it on paper. And we also said that the graphical techniques of vector addition, they really are great if you specifically don't really care much about precision. Okay, like you want a ballpark thing. You want to know whether it's, sort of to the left and up a little bit. You're happy to know that it's 50 newtons. You don't really care if it's 50, 51, 49, but just, to maybe one significant figure is all you want. So this is a great method for all of that. But there are more precise ways. There are ways, some people get freaked out by the thought that you would actually do something and you wouldn't know for sure exactly what it was. Well, let me show you today the mathematical way to do it. And we're going to use that whole IJK notation to be able to accomplish this. This is why I taught it to you, and it's if you've flicked much through the book, especially to the sections that I didn't specifically ask you to read, then you might see that the book says a lot more about the IJK stuff. I really tried to boil it down for you and not have you read specifically from those sections. Okay. Now the other thing, just to kind of remind you of the motivation here, the reason why this is a little bit tough, it might feel a bit tough, is that this is a new branch of mathematics for, all of you to some extent. Some of you are 1 or 2 years ahead of others, but for all of you, this is at some level a new kind of number, a new kind of math. So every time that you learn a new branch of mathematics, whether it be matrices, imaginary numbers, at some point as a kid, you learned about negative numbers for the first time, and that was amazing. You did imaginary numbers when you hit, maybe 10th grade. And every time you run into this new realm of number, you have to learn what you can and cannot do and the little quirks that each one of them have. So vectors are just like that. It's just a different kind of math. It's like directional math, if you like. And remember that we are only worrying about addition. We are specifically not really going to do subtraction, okay, which is not that hard, but it's just like negatively adding. And then we said as well that there are two kinds of multiplication. There is dot multiplication, and then there's something called the cross product. We are not doing any of it. And then we said that you just really can't even do division anyway. There's kind of cheating ways to divide vectors. You can certainly divide the magnitude of a vector. You could say you might have a 10-pound force vector, and then you just divide that by the scalar number 10, and that would give you a 1-pound force vector, in the exact same direction. But that's not really the division we're talking about. You can't really divide two vectors. All right, I'm going to stop talking about things that you can't do. Let's focus on what we can. And my last note before I show you this is that we're just going to say that if you're in the 9th or 10th grade versus the 11th or 12th, I am going to burden the 11th, 12th graders with just a little bit of extra stuff. I do want you guys to be conversant in the inverse trig functions. I'm not going to require this for 9th, 10th grade. 9th, 10th graders, if you want to watch and learn it, it's not like terribly difficult and you'll be doing it soon in your math classes, but I won't need you to do it in your assignments and things. So don't stress too much about it, but feel free to pay attention. And this is just the idea that, I said this in Angel's comment this last week, that you can have, like you could have tan of 45 degrees equals 1, okay? That's a full complete statement. And when I type in tan 45, I get 1 coming out of the calculator, okay? You might say that's one way that I know that that is true because the calculator told it to me. Okay, there it is, calculator telling me. But sometimes you have a different problem. Sometimes you have tan of some unknown angle and you already have the answer and you need to actually work out what is the unknown angle theta in this case. So to find that theta, you can't divide both sides by tan because tan is not a number, neither is sine, neither is cosine. Tan is just an example here, of course. This applies to all three of those functions. But instead of dividing by tan, you have to use what's called the inverse function. And there are two ways to write that. If you know what I'm talking about, this is just a refresher. If you have no idea what I'm talking about, you can stay fascinated, but don't freak out. Inverse tan or arc tan is the two ways we can say that. And this is when we have that ratio of sides already, and we want to find what the angle is, okay? Instead of what we've been normally doing where you have the reference angle and it tells you what the ratio of sides is. In this case, the ratio of sides was that 1. Now we're saying if you have the ratio already, like maybe you had a triangle and the side lengths were 6, the leg lengths were 6 and 6, that ratio right there, 6 to 6, is a ratio of 1. So when you type in on your calculator arctan of 1, what you're going to get back now as your answer is the 45 degrees. Okay, it's giving you the angle from the ratio instead of using the angle to find the ratio. And look at this, if you're a 9th, 10th grader, you are just in happy bliss. You don't need to worry about that. If you're an 11th, 12th grader, you're looking a little concerned right now. And I'm okay with that. All right. Let's pick up our football problem that we did last time. Going to get pretty good at drawing a football, I'd say. Our football had 3 vectors. And we had, the first one was this right here. We called this F1. The second one looked like that. That was F2. These were force vectors. And we're just going to say that each square stands for 1 Newton or 1 pound or whatever it may be. And this one is there. That one. And the question that we were doing last time was, what is the sum of all the forces? And we did it using the head to tail rule. We slid these things around. Look, I may as well just refresh you on it. We said, look, if we, I'll use purple. said if we put, what was it? You know, if we slid F1 to be over here, and then we slid F2 and made him over here, then our resultant vector would be right there. Okay, that's what we did last time. You can see how F1 and F2 have been moved around in a head-to-tail chain, because that's what it was called. It was called the sorry, that was supposed to be a hyphen. The head-to-tail rule. And the head-tail rule means they can be in any order, but they have to be in a head-to-tail chain. And if you can do that successfully, then the resultant in green there goes from the first tail to the last head. Okay. No, by the way, notice with this football that because all three forces kind of pulled in different directions, they actually sort of partially cancelled out. So the resultant ended up being kind of smallish. Definitely smaller than F1 or F3. Okay, that's a pretty common thing to happen. So if I can just get rid of those vectors, let's see how I can do this. Get rid of these ones. I have to redraw some stuff. We'll see how we go. Get that lacing back on that football. Instead of dragging these around graphically, we're now going to try to describe these three vectors using our I and J notation. Now, everything I'm about to say here would work just as well in IJK, but we're doing just 2 dimensions. Okay, so you could either do it in I, J, or I, J, K. Before we start doing any of this, we really should be absolutely sure that we all agree on what we mean by the directions of I, J, and K. Now, those who've had me before, which is almost all of you, know that I'm a big stickler for this. Sign convention. Sign convention just means saying from the start of the problem which directions are positive for which variables. Okay, you have to have that in agreement somewhere. So we just do this. We just draw a little tiny diagram somewhere nearby for a 2-dimensional problem. It could be as simple as this. You could say, you could draw a little sketch like this. You could say, all right, this is X, this is Y. And it's implied then that that's negative X and negative Y, although I don't actually usually even show those. That right there would be an example of a good sign convention drawing. It could even be simpler. It could just be like this. You could just do X, Y. Okay, that's more like what I'm going to typically do. Just pointing out that when I say X, I mean that it is horizontal and that positive is to the right. And when I say Y, I mean vertical on the page and up is positive. Now this might seem super obvious because every graph you've ever drawn, every Cartesian graph since 7th grade or even earlier, has always been just like this one right here. But sometimes we have other problems. If I can quickly take a sidestep here, sometimes we are like, pushing all right, sure, we'll take that. Sometimes we're pushing a wooden crate up a hill, okay? And because we have this inclined plane, sometimes it makes more sense to say, you know what? Let's call that X and let's call that Y. Like, let's actually align it to the plane that we're talking about. I don't know if that's, let me do that bigger just in case it's not totally clear what I'm saying. Okay, I want that and that, okay? That's my X direction, that's my Y direction. Very, very common for inclined plane problems. If you don't have an inclined plane somewhere nearby that's messing things up for you, then you'll generally just be doing it just like this one right here. Okay, so that is what we will do for today, and let me get rid of that. I'd love to get rid of it, but it's waiting for me to select it, I think. Okay. So let's define each of our 3 vectors. I'm going to keep the little one, by the way. I think I like it better than my uglier one. There we go. So I'm going to say F1, we can write that algebraically. And what we're really thinking about is what we call the components in the x and y direction, which are those I and j unit vectors. Which, yes, I know seem very confusing, but you know, once you get used to them, you just don't even think about them. So this f vector goes 1 unit, and it's this. I'm looking at this right here. Okay, 1 grid square. 1 grid square in the positive x direction. And so that is why I did this here. A positive 1i. And then in terms of the y, or the vertical direction, it is up by 4 units. So we give it 4j. And then I always do the units. I don't remember if I was doing pounds or newtons. This is an American football, so I guess I should probably do pounds. I don't remember a few days ago which one we used, but that should be right there in your notes. So F1 is written without having to draw any arrows, without having to draw any graphs, because we've defined x and y directions. We can say that arrow is 1i plus 4j, 1 unit to the right and 4 units up. A little bit like rise of a run idea, I guess, but not dividing them. Even better than doing it that way, I would just say I plus 4j. Okay? We don't normally write 1 in front of variables, do we? If you have 1x plus 2y, you don't normally write the 1x, you just put x plus 2y. Same idea here. We do treat the I hat and the j hat as variables. Let's give you the other ones, then I think this might start to become even clearer. For F2, starting with the horizontal component, we're going 2 units off to the left, which is opposite to what we defined as positive x. So that is going to be negative 2i. Okay, 2 units, but to the left, not to the right. That's why it's negative. And then in terms of the upness and the downness, we are going to go down by 1 unit. So it's going to be negative j hat. And then the units for the force, pounds. Okay, those are both negative. The first negative for the I is because we went to the left. The second negative for the j is because we went down and not up. Now we get to F3. Speaking horizontally first, we're going to go all the way across. That was 4 units in total. So we're doing 4 I hat. And then we're going down also by 4 units. So that is negative 4j pounds. So there you go. I've defined those 3 vectors, F1, F2, and F3, in their ij component form. Again, if we were in 3D, we could have had I, j, and k. It's probably true to say that all of these have a k component, but it is 0 in each case, so it doesn't need to be listed. Now, the advantage of doing it this way is that once I have them all listed in that ijk form, or ij form, I can simply add them, just as I would any other kind of variable. I can say, all right, sigma f, in this case, is f1 plus f2 plus F3. Then I just list off everything I have. In fact, I might even sort of do a, maybe let's do this. I can kind of put a sum right here. So, I'm just adding all of these, F1 plus F2 plus F3. And I look vertically down that column, and I have positive 1, minus 2, plus 4. Okay, which is 3i. And then I have positive 4, minus j, minus 4. Which is negative 1, like negative j, also measured in pounds. And that is it. I've got the whole answer right there, just like that, because I have them in that rectangular form, that's called, in IJ notation. I simply add the i's and I add the j's. And I can do that pretty easily now. I can just draw the answer from the diagram. We are going across by 3, and we're going down by 1. Therefore, it's right there. Okay, that is our resultant. Or that is our, actually here, let me use I'll say that is my sigma F, my sum of all forces. Okay. Now, if I wanted to know what the actual magnitude of that was, if I wanted to know what is the magnitude of the sum of all forces, look at this lovely notation you're learning, then we're going to do the Pythagorean theorem. 3 squared plus 1 squared. Notice I don't even worry about the negative because it gets squared, who cares? Doesn't really matter. Triangles can point up or down, the length won't be any different. And we get 9 plus 1, root 10. Root 10 on my calculator is 3.2. All right, 3.2, also measured in pounds. Now, like I said, if you are in the 11th, 12th grade, this is where I'd want you to also then use arctan. Let me do it over here. Let's use arctan just to find out what that angle is as well. And it's really as simple as this. You just do arctan of those two side lengths, the 3 and the 1. You can also do the 1 over the 3. It doesn't matter. You'll just get one angle or the other. You'll always get the two complementary answers. I'll show it to you actually. So arctan of 3 over 1 is 71.6 degrees. If you instead did arctan of 1 over 3, let's see, tapping it out, we get 18.4. Okay, those add up to 90 degrees. They are complementary. Complementary, not complimentary. They're not telling you nice things about yourself. They're complementary. Okay, and that's 71.6 or 18.4. It's a little tricky to see because my diagram got kind of busy, but in red maybe. I'll do the 71.6. That's referring to this angle right here. 71.6 degrees. Okay, how far it is up from the vertical line. Okay, so that is the whole problem right there. This part here, this part is just for the 11th and 12th graders to do. 9th and 10th, you're welcome to do it if you want. And that works because, of course, those two green horizontal and vertical components, together with the sigma f itself, they make a right angle triangle. So just to summarize all of that, we have to firstly list the forces with their their ijk components. Then you add it all by adding the i's, adding the j's, adding the k's if they're there. And this part right here, this line here is actually your answer, okay? That is your final vector in ij form. But then very, very often you want to know what the magnitude is, in this case, 3.2 pounds. And if you're going to go that far, you should probably do the angle as well, which was that 71.6 degrees. Now, by the way, compare this answer we got, 3i minus j pounds. Compare it to, I have ready from last week. This was, oh, that's weird. Oh boy, very odd. Sorry, I don't know why that did that. Let me, oh boy, anything could happen here. Okay, let's just move that out of the way. You can see this is the same as what we had last time. Oh, okay, I see it. Sorry, I did something different. I should have been more careful. Last week I defined it as being 2 newtons in each direction. This video we did 1 pound in each direction. But I think you can still see that the resultant R in the purple, okay, right here. Okay, let's try that again. Resultant R in the purple right here is the exact same kind of shape. It's across 3 grid squares and then down 1. This is just purely a screenshot from the previous video. Okay, I just wanted to show you that it still works. The angle is still 71.6 degrees. Okay, just like today's. And I got 6.3 because everything on this graph is doubled. Okay, right here you can see 6.3 is double the 3.2. Okay, that's what's going on there. Okay, let me do one more problem, just the exact same thing, just to reinforce this a little more. Let's find some clear space right here. And this time I'm gonna not do like simple ij components already. That one was really easy because we could read straight off the grid squares just what it had to be. This time it will not be quite the same. This time I'm gonna draw a picture of what we call, well, it depends who you are, but it's often called an eye bolt, as in the eye that you look with, E-Y-E. Okay, an eye bolt or sometimes called a screw eye or an eye screw. These are those, you might have seen them, they kind of get, like used to hang things on, and they have like a long shaft which goes into the wood. Okay, often used to hang things that are fairly heavy from ceilings or walls or stuff like that. So imagine this one is like buried into a piece of wood, and we are going to apply some forces to it. We're going to say that firstly, let's give it a 1,000 Newton force that is like 10 degrees off vertical. And let's just do one more. Let's do what would that be? Maybe a 500 Newton force. That's like 40 degrees up. All right, and let's call this one F1 and this one F2, just to keep them separate. Okay, so first thing you'd have to do here to find out the total amount of force happening to this eye bolt is you'd have to define the I and the J components. Let's just make our sign convention. Okay, X and Y. X is the standard one and Y is the standard one, up. So we need to define what those two components are, and you need to obviously do the same for F2. Now this takes a little bit of advanced work. If you're in the 11th, 12th grade group, I think you're very, very used to doing this. If you're in the 9th, 10th grade group, this is a little newer. So let's see. You firstly have to spot these 90-degree, these right-angled triangles. Okay, they're always there. They're always there. The vector always forms the hypotenuse. And then you've got those two legs. Notice that this leg is aligned with the y. Okay, notice this leg is aligned with y. Notice this leg is aligned with x. Okay, this leg is aligned with x. Okay, that's the whole point. We're trying to line it up with the xy coordinates system, the Cartesian system in this case. So you have to do the work now and do a little bit of sine, cosine kind of stuff. We're going to say, okay, what is sine of 10 degrees is, let's see, sine is SOH, okay, opposite over hypotenuse. So sine of 10 degrees is, if I have a good label for it, I guess I'll just keep calling it opposite. That's fine. Opposite over 1,000, okay, because 1,000, I should maybe actually move that. It might be easier to understand that it's the hypotenuse. Do the same over here. Okay, this is, I don't know if that's if that makes any more sense actually at all. Maybe it doesn't. Okay, sine 10 degrees equals opposite over hypotenuse. Now I'd say it's actually easiest here if you do a little bit of algebra. If you multiply both sides, by 1,000, and you suddenly have a pretty straightforward mathematical equation. Sine of 10 degrees times 1,000 equals 174. Okay, that's your opposite side length right here, 174 newtons. If you want the other side length, you're generally going to use cosine. Cosine is the second part of SOHCAHTOA, CAH, adjacent over hypotenuse. For those who are still doing this, I guess I could write this explicitly. SOHCAHTOA. I should remember some of you have only been seeing this for a couple of weeks of your lives. Okay, and cosine of 10, again, the adjacent we don't yet know, but the hypotenuse is right there in front of us. That is still the 1,000. You multiply both sides by 1,000, and you get that. We do the math, or the maths if you're in Australia, and we get 985 is the adjacent side right here, 985 newtons. Okay, so those were really, really important because that tells us now if we're going to write F1 with ij components, you start with the horizontal one. This is going to be, because it's pointing to the left, okay, opposite, like the other direction from what we called positive x. This is now going to be negative 174i, okay? The negative, really important. It's giving you that direction. And because it is up, which is the same as positive y, we do plus 985J. And then measured in newtons. Units always go on the end. Okay, we turned our 1000 newtons with a 10-degree angle into two components, the vertical, the horizontal, the I, the J. These two numbers, negative 174 and positive 985, those two pieces of information fully describe the other two pieces of information down there, the 1000 newtons with the 10 degrees. Okay, I'm going to erase all this and do that all over again for the other one. We're going to say, now we're going to be careful here actually, because the way I drew the triangle, I actually have the angle outside of, yeah, that green triangle, it doesn't have the 40 degrees inside the triangle. So at the risk of confusing you, I might just do a little bit of simple geometry here. This is the same angle, okay? This is the 40 degrees. For those who've done geometry, I just simply employed the parallel lines theorem with the alternate interior angles. Okay, but I think it's seems to me like a very intuitive theorem, but yeah, that's also 40 degrees. So I could even, probably just get rid of that. I think it's kind of clear what's happening. Speaking of clear, part of my eye bolts just went clear. It's going to annoy me. There we go. Okay. Yeah, that's all happening. All right. Okay, so we are going to do the sine and cosine thing here. We're going to say sine of 40 degrees, 40 is the reference angle, is the opposite over the hypotenuse. And the hypotenuse in this case is that 500. Maybe now if I do this, this will be a little better. There we go. I could have done a better job before of placing those. Sorry about that. Sine of 40 degrees equals opposite over 500. We multiply both sides by 500. And then we pick up the calculator. Remember, I really recommend a real calculator. I am not using one, and it drives me nuts. I'm using my computer's one. It's horrible. 321. So that is the opposite. Remember the opposite side relative to that reference angle, which is right here. 321 newtons. Then I'm going to do cosine again, because cosine is the adjacent. Cosine 40 equals adjacent over 500. That's the hypotenuse. Now, for those who are still fairly new to this, you might have noticed that we kind of ended up doing the exact same thing in all of these situations. 383. Right here, 383. Did you notice that for the 174, for the 985, for the 321, and for the 383, in each of those cases, we kind of had this same formula. We had the strength of the original vector. We had sine or cosine, and then we had that reference angle, which was given at the start. And yes, that is the formula which will always end up happening. Once you manipulate these SOHCAHTOA original formulas, you always end up with that. And it is acceptable to use that as a shortcut. Okay, strength of the vector, sine of the angle, and then strength of the vector, cosine of the angle. Just make sure you know which one is which. Is it the horizontal or is it the vertical? Is it the I or the J? Okay, now in this case, starting with the I, the 383, the horizontal one, it is pointing this way because it has to point the same direction as the original black vector. That matches with the positive direction of x. So we're going to put positive 383i. The vertical part is up. It is also matching to the positive y that we already defined. So we're going to go, again, positive 321 j newtons. Okay, and now we have them fully defined. That's the hard work. Now we can sum those vectors and say, you know what? The total force is 383 minus 174. And by the way, I'm kind of breaking one of my rules here. I'm doing it partly because of my dodgy calculator, but I rounded off to 3 significant figures. Even though I had more work that was going to be coming up, like this adding work right now, that is more stuff coming. And I know I said in previous lectures that you shouldn't employ any kind of significant figure rules until you know the math is all done. It's only in the last step you should do that. But it's kind of okay here because these original vectors maybe were only given to 1 significant figure. Maybe 2, maybe 3. Obviously it's not clear because I didn't use scientific notation, but if we maybe assume that they were given to only 1 significant figure, because I said 1,000, I said 500, then I used more than that. I used 3 significant figures in the kind of interim working. So when I get to the end, I've still kind of got some in reserve. So I think we're okay. All right, I'm going to add the 985 to the 321, 1306 j newtons. Okay, that's my final vector. Now, as far as drawing that, I'm not even going to bother actually. I'm not going to draw. I don't want to mess up the diagram too much. But I could also, remember, go the extra step and say, how strong is this vector overall? What's the magnitude overall? And I would use the Pythagorean theorem, which, pardon me, squared plus squared 1323, okay. 1,323 newtons. And then regarding the angle, I'm just going to do arctan of 209 over 1306. You're also patient to wait for me. We get 9 degrees. And I can tell because actually if I imagine grabbing that 500 Newton vector and sliding it up to go on the end of the 1,000 Newton vector, just like we did earlier this week with the head to tail rule and earlier today, I can sort of see where that would be. Like, can you imagine that? Can you imagine taking, here, I'll do it in like a light gray and then I'll delete it. I can imagine taking that and kind of, you know, it being somewhere. That is almost invisible, sorry. Try it again. Okay, imagine taking that. Didn't do a great job there, but it'll be something like that, which means the resultant would stretch like that. Okay, so that resultant is the one that we're talking about. That is the 1323 newtons, and the 9 degrees would be that 9 degrees from vertical. It's always going to be off vertical or off horizontal, and you just kind of pick it up from context since I didn't draw all the triangle diagrams and everything. And once again, this is the part that 11th and 12th graders need to do. Everything up to there is what 9th and 10th graders should be able to do. Now looking at this screen, This looks wild. You're doing a lot. So be proud of yourselves, be happy. And I hope that as you wrote this down in kind of a more linear fashion, as to what to do bit by bit, that it actually does make kind of sense. All we're doing is adding together vectors using their ij components now, or their ijk components. And that is not hard. That's just adding variables like you always have done. The only extra complexity is when you have to do this yourself, work out the components first yourself. And half of you, at least, are very, very used to doing it. If you already have the components, the ij components given, like in this problem, then it's even easier. You just throw it together, and then don't forget to work out the magnitude and work out the angle if you're one of the older students. Wow. Well, thanks for tracking. Good luck with the rest of the assignment, and please do ask me if you have any questions. All right, see you guys soon.